Yeah, thank you very much for the introduction and also for inviting me. So the situation is a little bit special because actually I stopped doing math and I haven't thought about these things in the last 4 months. So this makes me even happier that you gave me the chance to dive in again. And yeah, I want to talk about the nilpotent cone in the Mukai system of rank 2 and genus 2 today. And so I will just start by explaining what is the Mukai system. Yeah, I don't know where you all come from, like what your background is, so please feel free to ask questions at any time. So I'm happy to answer them. All right, so the story starts with a K-free surface, which I take to be polarized. And everything here is over the complex numbers. So the polarization will be given by an ample line bundle on S. I denote by H. So this is an ample class, but I want to think about this as a curved class. And so fixing the polarization allows me to associate a genus to the K-free surface. So I say it's of genus G. And this just means that so H squared is 2G minus 2. So I'm on a surface, so I have an intersection product for divisor classes. And this just means that any curve in this class has genus G. Okay, I want to fix 2 numbers, namely a natural number greater than 1 and an integer, which is I call S coprime to N. And then I consider M, which is the moduli space of stable coherent sheaves on S with fixed Mukai vector V, which I take to be 0 n times H comma S. So this Mukai vector is an element in the even cohomology of S, and it's just a way to fix numerical invariance of the sheaves I want to parameterize, so in order that this moduli space actually exists. And so this signifies that the first entry means that the rank is 0. So the sheaves I consider are actually supported on lower dimensional subvarieties, so curves or points. But actually, the second entry is the first Chern class. So it's non-zero. So all these sheaves I actually consider here are supported on curves. And the third entry gives the Euler characteristic, which I fix the S. And so in this notation, I also index H here, because when I say stable, I mean Giesecke stability, which actually depends on the choice of some ample class. All right, so an example of a point in this moduli space would be given by a line bundle on a curve linear equivalent to n times H. So take smooth curve in S, linear equivalent to n times H. So I write D in NH, the complete linear system. And then L of a line bundle of fixed degree. So I denote the inclusion by I. And then I lowers the L defines a point in M for the correct degree, of course. So just that the Euler characteristic is correct. All right. So I fixed N and S coprime, because in this case, M is actually smooth and projective. Of dimension 2 times n squared G minus 1 plus 1. So this you can compute from knowing V. And moreover, and most important, it's a Hyperkaler manifold. So, so this also goes under the name irreducible holomorphic symplectic manifold. So maybe you've heard this term before. And I also want to recall the definition. So this means that it is so X. So first of all, it's a smooth compact variety. With a symplectic form, so with a holomorphic symplectic form. So call this variety X, and then the holomorphic symplectic form I call sigma in H0 X omega 2. So it's in symplectic form, meaning it's non-degenerate, and it's unique up to scalar. So this means that actually the space of two forms is generated by sigma. And then there's the last property, X is simply connected. Okay, so this is the definition of an irreducible holomorphic symplectic manifold, and you can think of these as higher dimensional analogs of K-free surface. And actually, there's an also very rich theory, like as in the case, almost as in the case of K-free surface, which is of course still being developed in the Hyperkaler case, I mean. And
sorry, just a kind of a naive question. So the definition of a Hyperkaler manifold that that I've heard of is one that would have like 3 complex structures, corresponding Kaler forms, etc. This is somehow equivalent to that?
Yeah, it's also the same. True.
Oh, okay. So yeah. This definition, I see.
Yeah, so you have 3 3 Kaler forms that satisfy a certain relation.
Okay.
And 3 complex structures. Yeah.
Okay. Thank you.
Yeah. Okay, so yeah, so you have a symplectic form, and on this M I defined up here, you have a Lagrangian vibration. So.
All right. So what's the type of M? I mean, this Hilbert scheme of a K3 surface.
Yeah, it's exactly. It's a formation equivalent to a Hilbert scheme of point on a K3 surface. Yeah, and yeah. So for a certain the one we'll say later. So later I specialized to low dimension is actually birational to a Hilbert scheme. And here, yeah, definitely deformation equivalent, and for some choices of S and birational. Okay, and so yeah, I have a Lagrangian vibration on M, and so this will be the Mukai system because so what I call Lagrangian vibration. So this is a map where all the fibers are Lagrangian subvarieties. But you could also call it completely integrable Hamiltonian system. And so this is why this system term pops up. All right, so on M, we have a Lagrangian vibration, which is given as follows. So when you have a point here, you map it to its support. Okay, and so as I said before, these sheaves are supported on curves. And moreover, so I don't take a naive definition of Z-theoretic support, because this actually wouldn't allow me to define a map on the moduli space, because it's not well behaved in families. But what I take here is the so-called fitting support. So if you want to know the definition, you take a length 1 resolution by vector bundles, which you can always find for the kind of sheaves I consider. So this is E. And then call this alpha when the support of E is defined by the determinant of alpha. So V1 and V0 have the same rank because E has rank 0. And so this is well defined and actually independent of a choice of the resolution. Okay. And so as you see from the definition, you always get a curve with class C1 of E. And C1 of E I fixed to be linear equivalent to n times h. So here you get a map to this complete linear system, which is a projective space of half the dimension then M. Okay, so I want to give you a feeling of this fitting support maybe. So if you have something locally free of rank 1 on a, yeah, stay in our case on a curve, then the fitting support is equal to the set theoretic support. But if you have something locally free of, say, rank 2, then the fitting support will be 2 times the set theoretic support. Yeah, so what we see here is, so if we take a smooth curve in the linear system, then the fibers will just consist of line bundles. So actually, yeah, the fibers are these Picard varieties, so they are smooth and abelian varieties, so super nice. So general fibers, yeah, are very nice. And you can also think of M as a compactified Jacobian associated to this linear system. Okay, but you could also start with a curve in the linear system H, and then you can consider the nth thickening, so n times c. And in this case, in the fiber you have, so either you might have rank n locally free things support like on the reduced curve C, or you have sheaves that are maybe, yeah, rank 1 on n times c but have torsion or anything in between. So the upshot is this fiber is a lot more complicated, and actually it's not irreducible. So it consists of several components, and yeah, this makes it interesting to study. And I have a name for it. So this one, this fiber is actually called the nilpotent cone. And I abbreviated with NC.
Can I ask a naive question? I mean, why we call it nilpotent?
Ah, very good question. So yeah, of course, this is the first question that comes to your mind. It absolutely does not make sense at this point, but there's a meaning to it, and this I want to explain next. And namely, so where do you know this nilpotent cone may be from? So this is from this what is called the Hitchin system. And so this is sort of my motivation for the talk today. So one motivation, of course, out of many to study this Mukai system is that you could see it as a Hitchin system in the K3 world. And we'll see that, yeah, there's a sense that I call it nilpotent cone. So let me write this first. So the Mukai. So in the K3 or Hyperkaler world. All right, so I want to first recall the definition and some facts about the Hitchin system. And then I'll say, what is the connection? So yeah, I assume that most of you have seen the Hitchin system before, but feel free to ask. So the Hitchin system starts with a curve C of genus G. And again, I fix two numbers, n greater than 1 and d, which are co-prime. Okay, and then I study the moduli space of so-called Higgs bundles. So this is moduli space of stable Higgs bundles of rank n and degree d. So these are pairs E, phi, where E is a vector bundle on C and has rank n and degree d. And phi is a morphism from E to E tensor omega C. So
sorry, may I ask another naive question? So when you say co-prime, it's G and D are co-prime, or
no, N and D are co-prime. So I want, because I don't want to care about
but we don't care about whether G is co-prime.
No, not at all. Sorry. Yeah.
I see. Thank you.
Exactly. So so because I fixed N and D co-prime, this moduli space of Higgs bundles is smooth. So yeah, I mean, this is, so there is a stability condition on this pairs for Higgs bundles, which is a stability condition on the pair. So it does not imply that E has to be a stable vector bundle, but if E is stable, every such pair would be a stable pair. And yeah, the story is the same as for moduli space of vector bundles. So if you have ND co-prime, there's some numerical game that gives you that like semi-stability is as obvious as every semi-stability is the same as stability. So this modular space is smooth. And this modular space of Higgs bundles is not projective, but it is quasi-projective. And its dimension is 2 times n squared times g minus 1 plus 1. So maybe you've seen this number before. And it also has a symplectic structure. And comes with a Lagrangian vibration. So, and then this is what is called the Hitchin system. Okay, and so this Lagrangian vibration is given as follows. So you start with a pair E, phi, and you map it to the coefficients of a characteristic polynomial of phi. So, and then this, because you have this twisted endomorphism, so the coefficients of a characteristic polynomial are in this affine space, which is the direct sum over sections of tensor powers of the canonical bundle. And so here it's much more natural, what you call the nilpotent cone, namely the fiber over 0. So now consists of all those pairs where the characteristic polynomial is 0. So which is the same as saying that phi is nilpotent. And it's also cone, so you can scale phi by t. All right, so this is the nilpotent cone. And also in this setting, there's some natural motivation to study the nilpotent cone. I mean, not only that you have the same story here, you have that general fibers is smooth and like very easy to understand, but this nilpotent cone is much more trickier. And you have a C star action on the smaller space of Higgs bundles. So you could scale the Higgs field by some scalar. And then the C star action retracts everything to the fiber over 0. So this nilpotent cone is a deformation retract of a modular space of Higgs bundles. So it carries all the topological information. So for example, if you want to compute the cohomology of this modular space of Higgs bundles, you're good if you understand the nilpotent cone. All right. So are there any questions concerning the Hitchin system? Okay, so if this is not the case, when I go on and explain what I promised, so what is the link between this nilpotent cone and the Mukai system and nilpotent cone and the Hitchin system, or more generally between Mukai system and Hitchin system? So, and the answer is that actually there is a degeneration going on. So you can degenerate the Mukai system to the Hitchin system. And the first step here is to give a new interpretation of the Hitchin system. And this was discovered by Bouville, Narasimhan, and Ramanan in the late 80s. So what they discovered is that, so if you consider a set of Higgs bundles such that the characteristic polynomial of phi is fixed, say S1 up to Sn. So when this is the same as the set of pure, so pure just means torsion-free for smooth varieties, and it also makes sense on non-reduced things. So pure rank 1 sheaves of fixed degree, so I call it delta again, on a curve CS, which sits inside the cotangent bundle of C. Okay, so this is a curve which is defined by this tuple S as follows. So recall, so this is in so first of all, I have this cotangent surface, which is an affine bundle over C, so it's an A1 bundle. And in here I have the 0 section. So I write C inside T star of E, and I want to fix a section which defines the 0 section, so call it X. So X is in pi upper star of omega C. Okay, and then I define CS as follows. So CS is, which I need more space. CS is defined by polynomial x to the n plus pi upper star S1 times x to the n minus 1 plus pi upper star S2 times x to the n minus 2 and so on, times pi upper star of Sn. So this defines a curve inside the cotangent bundle surface. And so you can restrict the projection to this curve CS. I call it PS. And then you by definition, it's an n-to-1 covering of C. And actually, CS is linearly equivalent to m times the zero section. So the upshot of this discovery is that with this interpretation, the moduli space of Higgs bundles is actually a moduli space of sheaves on some surface, namely this cotangent bundle surface. And moreover, this Hitchin map, so the Lagrangian vibration from above, translates into the support map. Yeah, and I can also say how this correspondence is established. Sorry, I forgot this. Maybe. Oh. So this is an n-to-1 covering over C. So if I start with a line bundle, here, so if CS is smooth, so then what I wrote where it just means line bundle, and so I push it forward along this n-to-1 map, so I get something of rank n, which will be E. And then I need phi from pi s lower star L to pi s lower star L tangent omega C. So here you apply the projection formula and a junction, and you'll see there is a canonical way to define phi. Okay. So yeah, so now we saw that M Higgs is actually a moduli space of sheaves on surface. And what we do now is we degenerate the K3 surface we had earlier to this cotangent bundle surface. And then we take the relative moduli spaces, and what comes out is the degeneration from the Mukai system to the Hitchin system. Okay, I make it precise. So step 2, is the actual degeneration. So this was done by Donagi, Ein, and Lazarsfeld in the late 90s. So now what you do is you start with the K3 surface S, containing curve C. So this is now our situation. And I want to, but again, I want to take that the class of these curves defines me polarization. So I take this C as a hyperplane section. Okay. And then what I can do is I can degenerate S to this cotangent bundle surface. So this is not a mystery, but can be written down quite explicitly. So probably you've seen this. It's called the degeneration to the normal cone. And what you do is you write down so a relative family over P1, which is given as follows. So you start with S times P1, the trivial family, and now you blow it up in C times 0. So 0 is just some fixed point in P1. Okay, and then I want to take out, in the exceptional divisor, I take out one component, namely the strict transform of S times 0. So what I get is this relative surface where over T non-zero, nothing happens. So I just have a trivial family, and so I see S here all the time. But when T is 0, I have the exceptional divisor, which would have two components, but one I took out. And so what stays is the normal bundle, so the projective bundle of this normal bundle of C times 0 and S times P1, which is omega C plus O. But then I took out something which is the section at infinity, and what stays is cotangent bundle. Yeah. And moreover, what is quite nice is that all the time I can embed C. Namely, here I have an embedding of C times P1, because this is just the same as blowing up C times P1 and C times 0. So I can embed it here, and I have constant embedding of C throughout this deformation. Okay. So now it's clear what to do. I want to take relative moduli spaces. And all I did above now fits in this picture. So you have my relative moduli space, relative base space, and such that over T non-zero, I see the Mukai system. And over T equals 0, I see the Hitchin system. So I call the base B. Is it? All right. Where here, so now I need to take V as 0 and H. And now if I fix ND on the Hitchin side, here I have Euler characteristic N plus D times 1 minus G. No, sorry. Oops. D plus N times 1 minus G. Okay, and moreover, because as I said, you have this constant embedding of C in there, what you also get is that the nilpotent cone on the Mukai side degenerates to the nilpotent cone on the Hitchin side. So yeah, this lays out a strategy to study the Hitchin system, if you want. Namely, what I want to do is I study the Mukai side, and then I transfer results to the Hitchin side via this degeneration. So I want to say two remarks about this degeneration. So namely, you notice that at no point here I used that as a K-free surface, so it actually works for any surface containing C. But so I want to use a K-free surface because just my theory of a coherent moduli space of coherent sheaves on a K-free surface is super nice. So it works for any surface containing C. And maybe you've seen this paper like more than a year ago where Cataldo, Maulik, and Chen proved the P equals W conjecture by using this degeneration. So and they start with an abelian surface containing C.
Wait a minute. I don't think they totally proved the P equals to W conjecture, but just for the genus equal to 2 case, right?
Yeah, they only proved it completely in the genus 2 case, exactly. Yeah. And they almost proved it in
the they almost proved it. Yeah, that's true.
Yeah. There's a little step missing at the end. Okay, and another thing, so this deformation is a little bit strange because so here this map is not proper. So as I said, yeah, this modular space M is projective, but the modular space of Higgs bundles is not. So okay, this cannot be a proper map. But you could also degenerate S to a compactified cotangent bundle if you want. And this is also a nice idea because it gives you a natural compactification of this modular space of Higgs bundles. But so you have this C star action on M Higgs, as I said. And so there are no compact symplectic spaces with C star action. So if you compactify, you lose the symplectic structure. Yeah, but of course there's moments where you want to do so. Yeah.
Just a quick question. So you said that the symplectic structure is lost.
Yeah, because the C star action is preserved.
Right, exactly. But is any like semblance of the Poisson structure still there? Sorry, I got ahead of myself. Any semblance of the symplectic structure still there? Like maybe something Poisson or?
Yeah, I think yes. I think modular spaces of sheaves on projective bundles. No, on. Yeah, I think the surface is a Poisson surface. This projective bundle, could this be? No. Yeah, I forgot. But there is a paper by Markman about Poisson structures. Okay, whatever. There is some special case which is fulfilled here, and I think you have this Poisson structure. Okay. But maybe someone else knows better than I do. Okay, so what I want to do the strategy for is to study the nilpotent cone, as the title suggests. And so today, study yeah, and unfortunately, also in the Mukai system, it's still quite complicated to study in high dimension. So this nilpotent cone gets more complicated for higher n and higher genus. So what I want to do is actually I start with studying the lowest dimension. And this is I fix n equals 2 and g equals 2. So this is what rank n and genus 2 refers to my title. And then I also fix degree, or what I called it, s equal to 1. But this actually does not matter. So I just need some odd integer here. Okay, so this means now I deal with a 10-dimensional space. So this is 10-dimensional, fibered over with linear system 2 times h, which is 5-dimensional projective space. Okay, and so I have the following theorem. So I take a curve in this linear system, which is smooth. And then, so I defined earlier the nilpotent cone to be the fiber over this non-reduced curve 2 times c. So then NC has 2 irreducible components, N0 and N1. So this is a decomposition into irreducible components. And I know what their degrees and multiplicities are. Namely, the degree of a first component is 5 times 2 to the 9. The degree of a second component is 5 squared times 2 to the 11th. And for the multiplicities, I have the multiplicity of the first component is 2 to the 3, so 8. And the multiplicity of the second component is 2. So it only makes sense to speak about degrees when I have some fixed ample class. So, and I do fix one here. So there, the degree is computed with respect to a fixed ample class I call U in H2 of M, comma Z. And more precisely, I define it as follows. So I take a universal sheaf on M times S. So this comes with two projections to M and to S. The one I call P and the other I call Q. And then I can consider the Chern character of this universal sheaf, which is on M times S. I multiply with a class coming from S. So this is comes from S. And so this is now still on M times S, but I push it forward to M, so I get something on M. And now I take the part 2 cohomology. So this is an H2 of M, comma Z. And this is my class U. And okay, there's some choice. I want to choose X such that U is ample. And because I have quite a good understanding of the cohomology of Hyperkaler manifold, I know what to take here to find an ample class. All right. And yeah, later I want to, I will say how to prove this theorem, but before I have two more. Namely, we have the same theorem for the Hitchens system. So you translate everything. Okay, and actually, so here, the description of the components is very well known. So this is nothing new. And also the multiplicities are also known. So this goes back, yeah. So many people computed this. So I think the first was for Dios, also in the genus 2 and n equals 2 case, and then there's resolved by Hitchens, which is more a differential geometric approach, also for genus 2 and no, for n equals 2. And there's recent project by Tamás Hausel for any n. So, and yeah, so they all compute the multiplicities, but actually, so no one has thought about the degrees so far, which is actually interesting because in my case, I compute the degrees first, and then I can conclude what the multiplicities are from knowing the degrees. And so to prove this theorem about the Hitchens system, so you have to know this description of the components, and then what you can show is that actually, so not only the nilpotent cone deforms, but every component, so the smooth locus of every component deforms. And so this way you can conclude that multiplicities and degrees stay constant. Yeah, which is quite nice. And And so I have more and more theorem about this about these components of a nilpotent cone, which is actually now does not fit into my slogan for today anymore. But yeah, it's also interesting if you care about Hyperkaler manifolds. So so this is a statement about the cohomology classes given by the two components. So these are subvarieties of codimension 5. So they define a class in H10. And I want to take the vector space, subspace generated by these two classes. And the statement here is that they are linear independent. So this is two-dimensional subspace and totally isotropic with respect to the intersection pairing on H10. Moreover, I can also give a more precise description of the classes, namely N0 I can write as 1/48 times class of a general fiber plus some class beta, and N1 is 5/12 times the class of general fiber minus 4 times beta, so the same beta is above. So first of all, so this is the class of general fiber. So they all have the same class because all points in P5 have the same class. Class of general fiber. And so beta is first of all non-zero, and it's not in the fifth symmetric product of H2 of M cubed, but in the orthogonal complement. And it satisfies beta squared equals 0. Okay, so yeah, this has nothing to do with the Hitchin system at all, but yeah, it's maybe an interesting result if you care about cohomology of Hyperkaler manifolds. So for example, you could ask what subspace is generated by classes of Lagrangian submanifolds also. All right, so I want to use the rest of my time to say some words about how to prove this theorem 1, because actually the other results are also based on this computation I made here. So yeah. Okay, so the first step is to get hands on the component. So I need some description. And first, so there is fact about fibers of Lagrangian Lagrangian vibration and Hyperkaler manifolds that fibers are equidimensional. So I don't have to worry about this. So if there are 5 components, if there are several components, they all have dimension 5, and hence are Lagrangian submanifolds. But so what we want to see is that NC is reducible, as I claim. So yeah, as I said before, there is one component that's easy to detect, namely we consider the moduli space of stable vector bundles on C of rank 2 and degree 1. So as I said before, so something of rank 2 on C defines a point with fitting support 2 times C. So, and I chose the degree correctly such that the other characteristics match. So I have found a subvariety of the nilpotent cone. And what I know about this subvariety is that it's irreducible and 5-dimensional. So actually I found an irreducible component. Okay, but of course there are more sheaves that are like rank 1 on C, but may have torsion. And so what I claim here is that actually these form an irreducible component as well. So the rest here, the remaining space is irreducible. So I take sheaf here. And then what I can do is I can restrict it to C. So I didn't take anything of rank 2. So this will have rank 1 on C, but acquires torsion. So I mod out the torsion. So this will be now line bundle on L. Yeah, line bundle on C, which I call L. And so this map is surjective. And I consider the kernel here. So, and actually, so this sequence here comes from considering just the restriction to C, and then the kernel here is the co-normal bundle. So what you find is that the kernel is actually given by I lowers of L, but now you have to twist with the support of the torsion. So otherwise, yeah, this is not injective, and you tensor with. So this is what the kernel is given by. Okay, and now the point here is that so E was a stable sheaf, so this means I have some inequalities for the subsheaves, and it actually gives me, it forces that I don't have any choices for the rank, for the degree of L and the degree of the support of the torsion part. So I find that the degree of L has to be 1, and the degree of the torsion part is 1. So this is actually only true for genus 2. So in higher genus, you would find degree between 1 and G minus 1. So in this case, you would find G components, but so here in my genus 2 case, it's all very nice. I only have 1 extra component next to the vector bundle component. So yeah, the degree of a torsion part is just 1, so this is nothing but a point. And this means I can parameterize these extensions by some projective bundle over pig1 of C times C. And what I find is that so this gives me actually a birational map into the component. So the thing is that so it's actually outside of the intersection of N1 and N0. This map will restrict to an isomorphism, but on the boundary something happens, and also this N1 has singularities there in the locus where it meets N0. But what is more interesting to us at this point is that so this is actually an irreducible space versus 5-dimensional. And this concludes the proof that yeah, I only have one extra irreducible component. Okay, so now I'm ready to compute the degrees. And the key here is that the definition of this ample class U was so functorial. And yeah, and I now have a moduli description of the components, which I can use to compute with degrees. So namely in the case of the first component, so what I have to compute is I want to integrate u to the 5 multiplied with n0 over m, so which is the same as restricting u to n0 and integrated on n0. Okay, oops. So I have to find out what is u restricted to n0. And so this is yeah, where my functorial description comes in. And so it just, yeah, essentially I plug in the definitions. And what I find is that I get 2 times the theta divisor. So of course, the scalar here depends on the choice of the ensemble class. So I could also find a multiple. And this is the theta divisor on this modular space of vector bundles. So this is just a generalization of the theta divisor, you know, for the Picard scheme. So if you fix n and d such that the order characteristic is 0, then this is the jumping locus where h0 is non-zero. So h0 minus h1 is 0, but there's a codimension 1 locus where h0 jumps, and this is the theta divisor. Yeah, it's also so if you fix the determinant, then this class is a generator of the Picard group of a modular space of vector bundles with fixed determinant. Okay, and there's lots of this, yeah, several computations with this theta divisor in the literature, and especially you know its degree. So this now is 2 to the 5 times the degree of the theta divisor. And yeah, I know what this is by from the Valinde formula. This degree is known, and you find the degree. You find d0. All right, and so for d1, yeah, the story is the same. So now n1 itself is not smooth. So I don't want to restrict to n1, but I use this map nu I had above. I restrict to n1, pull it back, so it's a birational map. It doesn't change the degree, and then yeah, I have to find out what is this pullback, and I can do it because I use that nu is given by some universal extensions, and yeah, so I want to find something in H2 of P of some yeah, some projective bundle, and so I know the cohomology of projective bundle, and so it's technically a little bit more involved, but yeah, it's possible to compute. And so you find the result for D1. So what's missing to complete the proof of the theorem is our multiplicities. And here, I have to admit, I was very lucky because actually it suffices to compute the degrees. So the trick here is that, so general fiber F is smooth, so its multiplicity is 1. So what you find is that the degree of a general fiber is just the product of m0 d0 plus m1 d1. And for the degree of F, you do a similar computation as for D0, or you could also use the Bouville-Bogomolov form if you want. So what you find is so 5 times 3 times 2 to the 13 is equal to what I computed above. Just spell it out. And now the point here is that so the degrees are quite big, and the only solutions of these equations are for small m. So there are only 2 possibilities, namely either 81, 28, 1 or 8, 2. And so here I have an m0 is 1, meaning that one component is actually non-reduced. So, and I can prove that this is not the case by computing the tangent space. So this nilpotent cone is like a moduli space of sheaves on this thickened curve. So the tangent space is some X group. So the first X on this thickened curve in this point E. So where E is in this N1 component. And I can compute this X group to be bigger than the dimension of a nilpotent cone. So this implies that N1 cannot be reduced. So I'm very lucky here. This solution is ruled out, and I know what the multiplicities are. And this finishes the proof and my talk. So thanks a lot for listening.